Okay, welcome to the thermodynamic signs lecture. So we're going to start with our beautiful Gibbs free energy equation, and we need to understand what the signs of all three really mean. So let's start with delta H, okay? So delta H, and you may want to take some notes here, but it's important you know this, delta H, and you probably know this one. Delta H, if the value is negative, that's an exothermic reaction, okay? And exothermic, of course, means that my Q is negative, all right? And more importantly, energy, thermal energy, is released into the environment. Okay, when delta H is positive, this is an endothermic process. I should say process because there are chemical reactions and physical reactions, phase changes. Q, of course, is positive. Okay, energy is released, and energy is absorbed. I'm not a big fan of using energy absorbed because that may think that the chemicals are getting warmer, but sometimes you have a block that absorbs energy, gets warmer. So you can use absorbed. I'm a big fan of um, consumed. You're using the energy to do something. Now, it's very important you realize that these values alone do not measure spontaneity. All right? Just because energy is released, this is not free energy. It's just thermal. So we're not measuring free energy, it's just thermal energy. However, you should realize that this quantity is really measuring the what? The delta S of the surroundings. I think I've driven that home. Okay, now, so you got this down. What about this is, and I'll put this here, this was, and I'll put it in red because I'm in red today. This is enthalpy. And of course, it's a thermodynamic quantity that describes when what? The pressure is constant, the thermal changes, okay, in a chemical reaction or a physical phase change. All right, then we have entropy. We have enthalpy, entropy. It sounds similar, but it's different. In fact, let's write it in blue, okay? And I do that because that's an important one, okay? That ties us directly into, okay, the universe, second law of thermodynamics. So let's go entropy, which we should know is delta S. If our delta S is positive, okay, that means that my entropy is increasing, which means that the what? Because we're probably usually measuring the system, we say that the molecular disorder is increasing, that the degrees of freedom are increasing, or we say there's an increase in the dispersion of energy or increase in disorder. They all mean the same thing. Increase in the dispersion of energy. Okay? Now, if delta S entropy is negative, the entropy is decreasing. We have a decrease in disorder, right? Which really means that we're concentrating energy. Okay, like what? Like when we make glucose from the light and CO2 gases become glucose solid, boy, the delta S is decreasing. That's why photosynthesis is non-spontaneous. Now, entropy is important because the second law of thermodynamics, okay, states that the delta S of the universe must be greater than 0. Increase for spontaneity. So we have to consider that. Now, we really measure through tablature the what? The delta S of the system this way if we have tables. But we should know what this means. Okay. Now, really our delta S measurements from tablature is this guy right here, and that, of course, is the delta S of the system. And we know that this that we measure here is the delta S of the surroundings. Okay, and of course, we have Gibbs free energy. We need a new color. All right, and so we're going to do Gibbs free energy. Okay, and that, of course, is delta G. Delta G is negative when we have a spontaneous process, which means the delta S of the universe, okay, is increasing. And of course, there's free energy available to do work because the process is going forward without any input of energy. And we can ride that energy pony, and have our hair flim back, okay, and we can go somewhere. Now, if delta G is positive, we are non-spontaneous. And that means that delta S of the universe is what? Decreasing, which means we are concentrating energy, okay? And this doesn't work unless you do what? Force it. We have to have an input of energy to force the process. The best example I usually give is a spontaneous process. I'm riding the energy pony. I'm riding the pony. It's taking me somewhere. It's free. I don't have to use my legs. But if I have to carry the pony and add an input of energy to force the pony to get somewhere, I have to supply free energy, not get it. So this is, getting free energy. This is supplying it. Okay. Now, another great example is that a battery has a delta G that's negative. It, when set up correctly, gives us free energy to power our devices. But once it dies, we have to plug it in and recharge it. Recharging a battery is non-spontaneous. We have to add voltage, add energy to make that happen. Okay. And we have one more important value of these three, and it's delta G. And this is important. Delta G is equal to 0 when there's no more work that can be done. And this is weird, but it's not. It's really tied to something I've taught you. Delta G, when there's no more favorable direction. Remember, the forward reaction is very negative. The reverse doesn't happen. Remember when I burned a piece of paper? Okay, the combustion of the cellulose is very spontaneous. Why? Because the reverse just doesn't happen. CO2 and water don't recombine to form, okay, cellulose. So if the forward reaction is really spontaneous, the reverse isn't. But what if there was a process where we reach equilibrium? If we're at equilibrium, and we know at equilibrium, the forward process happens as fast as the reverse process, there is absolutely no favored direction. So if delta G is negative, the forward reaction is spontaneous and the reverse isn't. If delta G is positive, the forward reaction is what? Non-spontaneous, but the reverse is spontaneous. If delta G is 0, there's no pathway. Okay, so let me review that. There's no preferred pathway at equilibrium. So again, delta G, if it's negative, that means the forward process is spontaneous. There is a pathway, but the reverse is not. If delta G is positive, the forward is not favored, but the reverse is. And if delta G is 0, neither the forward nor the reverse process, okay, is favored because there's no direction anymore. And that, of course, is at equilibrium. So it's important that we get that down because we should have remembered a very important what? And I do this because people hate this diagram, but here it comes back. Oh my gosh, Oshkosh, here is this formula. And we have 100% reactants, 100% products. And this position here is equilibrium. And I've taught you before that all reactions work toward equilibrium. The farther that we're away from equilibrium, the greater the spontaneity, the greater the negative delta G. So if I'm in this position, okay, I'm so far away from equilibrium, I'm a high negative. And I move toward equilibrium. As I get toward equilibrium, delta G becomes less negative until it becomes 0. If I'm in this position where I have more products than I'm supposed to have, the reaction in the reverse, and I'll do that with a different color, so let's make sure we understand that. So if we are in this position, okay, maybe, okay, cool. If I am in this position, I have more products than I'm supposed to. The reaction is going to move in the reverse, and delta G of the reverse, okay, is negative, which means delta G of the forward is positive. And it keeps going until the delta G becomes less and less negative and eventually becomes positive, and that's the death of a reaction. All right, the process at this point, delta G becomes 0. And no, even though there is some movement this way and this way, the pathways are now essentially equal, and now there's no preferred pathway. Okay, very, very important. Okay, we're going to move on to the last page, I believe, of your read-along, so let's go there. All right, so we're going to go to the page where you see the delta G and equals delta H minus T delta S, this beautiful thermal equation for Gibbs free energy, and you see these little guys happening right here. So let's move on and let's talk about, now that we know the signs, we can actually look at what I call the sometimes, always, and never rule. Let's do the always rule, okay? And maybe that's a little bit too big. So let's get rid of that. And here we go. So this is going to become the always rule. Now what I mean by always rule is that you're always going to be spontaneous because you're always under these conditions going to be a negative delta G. All right, so delta G in this case will always be negative, okay, and thus spontaneous. Now, what is these conditions? Well, when delta H is exothermic, okay, so when delta H is negative, heat is being released, and when delta S, okay, is positive, that of course that we understand is the entropy is increasing. So when delta S is positive, okay, what we're going to get is the following. Now don't forget there's a negative sign here, and so what we get is a negative, and what we learn in math, a negative and a positive, you do plus the negative, right? So a negative plus a negative always gives me a negative delta G. So if I have something where it's negative delta G is negative, exothermic, and the delta S of the system, right? These are all system values. That's the degrees of freedom of the molecules is increasing. Okay, these are both favorable conditions. Okay, thermodynamically releasing energy and increasing the degrees of freedom of my molecules. That's also releasing energy in a sense. Both of these are contributing to an increase in the what? Delta G of the reaction. Don't lose sight. This is really measuring the delta S of the universe. Okay, and we know that that's increasing when delta G is 0. So anytime the reaction is exothermic and delta S is increasing for the system, we will get an overall increase in the universe. That's the always rule. All right, here's the never rule. The never rule is the exact opposite. This means the reaction will never be spontaneous. The delta G is positive, right? Because in this case, I'm going to have a delta H of my system to be positive, which we know is endothermic, and that my delta S will be minus, which means my delta S of my system, my molecular degrees of freedom, is going to decrease, okay? And these are bad, bad, bad thermodynamic quantities because both of them will contribute to the universe's entropy to decrease. In this case, both of these values will contribute to an increase in concentrating energy, okay? Not increasing the free energy, you can't do that. But this is a non-spontaneous process. Now, I put a negative here. Now, I know I didn't put the temperatures. The temperatures are kind of written here. But what do we know by negative, negative? We do plus, plus. So a plus and a plus, having a negative value here and minus that negative value really becomes a positive plus a positive, and you'll always have positive delta G, which means you'll never be spontaneous. So something that what takes energy from the surroundings, and something that where the system is losing, okay, free energy in the sense that you're concentrating energy, both of them contribute to the delta S, okay, decreasing. All right, now we have the sometimes rule. Sometimes, and there's two of them. So let's go through that. Here's a scenario where we're going to be exothermic again. The delta H is going to be negative. Energy is being released in the environment. That's a good, favorable thing. And then the unfavorable quantity is delta S will be negative. And we're going to put a negative sign there. And so let's think about a condition where we release energy and our system is getting more ordered and structured. Okay, so what is exothermic, yet we're getting more order and structure? But here's an example. H2O, okay, liquid becoming H2O solid, freezing. We'll put the energy here. It's endothermic. Oh, sorry, it's not endothermic, it's exothermic. So the energy would go here. Sorry, my bad. All right. So it's exothermic. Why? Because if you remember our what? Our energy diagram, a liquid becoming a solid happens right here, right? This is the liquid and this is the solid. And so we're going from high energy to low energy. So liquids to solids are releasing heat as something freezing. Freezing is exothermic. Okay, so that's good. We release heat. But wait a minute. A liquid going to a solid, we should be able to evaluate that as a decrease in entropy because we're putting molecules closer together. We're concentrating. We're going against the universe. So the system's entropy, molecularly speaking, is decreasing. So we have a good, all right, thermodynamic quality, but a bad one here. So we have one of each, unlike the always really have two good conditions, and here you had two bad conditions. Here we have one bad condition and one good. And so what we're going to do here is we're going to put this negative here. And if you notice, negative negative is a plus plus. So what does this mean? This can only be negative if this value is negative enough, which means we better release energy enough to overcome the system's decrease in entropy. We better increase the entropy of the surroundings enough by getting the gas molecules to go faster to overcome the system's ordering. And so this is only, okay, sometimes only spontaneous if this positive is small enough. Remember, there's a tease here. Temperature. When does freezing occur? Does freezing occur at high temperatures or low temperatures? Freezing occurs at low temperatures. So when T is low, it makes this positive expression what? Low enough that this negative is now big enough, and this is spontaneous. So only at low temperatures. Okay, freezing doesn't always occur for water. It occurs when the temperature is low enough. That's why it's a sometimes rule. And we call this reaction where the exothermic process drives a bad entropy process. This is enthalpy driven. So even though our system is becoming more ordered, more concentrated, okay, because we relieve enough energy to overcome that, it's an enthalpy driven reaction. It's sometimes, okay? So another sometimes condition is where we have a what? Endothermic, delta H, and a what? A good condition, a positive, okay, delta S of my system. Okay, and don't forget the negative. All right, and there's a T there. T comes involved with this sometimes. Now, if you notice here, do the math, a negative positive is plus the negative. Okay, so we have a positive and a negative scenario again. But this is a bad thermodynamic quantity, okay, right here, and a good one here. So the only way that this can work sometimes, if the system's entropy molecular increases enough, becomes disordered enough, higher degrees of motion enough in the system to overcome the energy that the surroundings lose. Right? So this is bad, this is good, but this has to be big enough. So where is an example, another phase change really helpful here, where something is endothermic, but the system is increasing? Well, how about H2O? Okay, gas, I'm saying liquid, let's do it that way, go to H2O what? Gas, heat of vaporization. Hey, liquid going to a gas is a tremendous increase in the system's entropy. That's why it's positive. But a liquid going to a gas requires energy. Remember the heating curve, right? So heating curve, liquid going to a gas requires energy. So that's bad, okay? Remember, so it's endothermic. But guess what? This temperature better be high enough to make this positive, or this expression that, I should say now, negative enough, right, to overcome this positive. And so this would be, if this is high enough, temperature is high enough, things can what? Evaporate. So this is only only negative if temperature, okay, in this case, is great enough to make it negative. Or if the system's what? Entropy is great enough. So if this is big enough, it'll overcome this poor thermodynamic endothermic loss of energy by the surroundings. And we say if this works, this is an entropy driven reaction. Okay? And you'll hear those terms. Now I gave you a scenario where temperature plays a what? A part in the phase changes. But there are going to be scenarios where something that the temperature doesn't play, where in this case, it's so exothermic, it overcomes the system's poor entropy, or the temperature stays constant and the what? The system's increase in entropy overcomes the poor endothermic quantity. So it's not always going to be about temperature, but these are the sometimes rules. And if they do work, the what? The good I should say the good thermodynamic quantity overcomes the bad if it's big enough. If it doesn't, then of course it's going to be a positive delta H and they don't work. Okay, so please get that down, get that in your vocabulary. Enthalpy driven, entropy driven. Play this again if you didn't see it. It's important to understand these signs and what they do to the overall reaction.